Just a reminder, our next test is a week from Wednesday, so that's the 27th. A lot of you have already responded to the survey I put out, so thank you for that. Unless something really monumental changes, I'm pretty sure we're going to do a Sunday night from 6 to 8. Seems like that works for quite a bit more of you than anybody else. So just a reminder, I'll remind you again as we get closer to the weekend, but and then I have office hours every Tuesday online from 3 to 4, and and Friday from 2 to 4 upstairs. So if you need anything, please come talk to me. If none of those times work for you, send me an email and I'll talk to you. But yeah, 1 week from Wednesday is the next test. If you go to Canvas, I already posted yesterday another document with a bunch of practice problems from the textbook that you can look at if you need more practice. Anything else? Okay, remind me before you go, I got quizzes. If you want them back, just hang out and I'll get them back to you. So one thing I know I forgot to tell you about the test is that it covers up through chapter 3. So we're going beyond that right now. We do have a third midterm this semester, so you will be tested on this before the final, but not this coming Wednesday. So first 3 chapters, or go ahead, Sebastian. But it'll probably emphasize things that didn't land on the first 3 tests. So the first chapter 1 was all about limits. Chapter 2 and 3 were about basically differentiation. So how to take derivatives, what they mean. Chapter 4 is really all about applying those things. So what can we do with derivatives now that we know how to take them? So especially because this is a section of Calc 1 for engineers, optimization is a big thing that you're going to be dealing with throughout your future math classes, your engineering classes, your careers in industry. But just a few things that you might use optimization and calculus to help you figure out, or that we've figured out using calculus. Basically, what's the maximum acceleration of a spacecraft, both that it can withstand and the people within it can withstand. I know I've had to make use of the second one. What's the largest size TV I can put in a room without it being blurry? How many customers should a business have every month to maximize profit? Kind of seems like you should just, the more customers, the better. Sometimes that actually hurts you. So a lot of these things can be, you need to find the best case scenario because there are constraints you have to think about. So step 1 and talk about that. If we're looking at case or worst case scenario, is going to talk about maximum and minimum. So you may know these terms, absolute maximum and absolute minimum. Did I record? Okay. Don't remember doing it. Okay. So I'm not telling you what the terms absolute max and absolute minimum mean. You may have it from elsewhere, but let's just see what you think. Based on what those terms sound like they mean, for this function I'm showing you here. Camera? Okay, so maximum 5. Okay, so we're revising from y value to xy coordinates. Look at agree with that. Why is 3.5 the absolute maximum? Sebastian? So what would you suggest otherwise? That's not a point. Okay, so depend on the situation. If I'm asking, I was purposely vague here. I may ask you for a point. I may ask you for the x values given. I may ask you for the f of x values that are maximum and minimum. But yeah, in this case, I was intentionally vague. So let's put some let's put some specifics behind it. What do these things mean? So let's C be some x value. So C is a number in the domain of a function. Then absolute maximum and absolute minimum are this. And this probably answers the question you just asked, Sebastian. F of C is the absolute maximum if it's at least as large as f of x for every other x in that domain. Similar idea for absolute minimum. I just copied and pasted it. Changed the word, changed the sign. So it's the absolute minimum if everything in the domain is at least large. So by no means this is wrong. You just might have given me more information I needed to, but you gave me what I wanted. People have seen before? A couple of head nods, a couple of head shakes. Synonyms, you might also like collectively. I might use the word extrema to describe both of them collectively. Or instead of the word absolute, you might say the word global. Any questions so far about how these things are defined? All right. So I want to find the absolute extrema and the another term I'm not going to unpack for you quite yet, but let's talk about the one that we have talked about. So let's look for absolute extrema. Based on this graph I'm showing you, what would the Thomas, you have a question? Or go for it. So think back to the definition we just gave for absolute minimum and absolute maximum. What value do you like? Hard to say without using at least, but what information is required? Yeah, it's really the y value, right? So yeah. So I mean, they clearly occur at x equals d and x equals a. So absolute maximum at f of d and absolute minimum at f of a. Are we okay with those? All right. How about this new thing that I haven't really defined yet, just to kind of see where you are? So we have the absolute extrema, which looks at the greatest value of y over the entire domain and the greatest and the least value of y over the entire domain. Now we're looking at local. So let's start with maxima. What values up there would you say are local maxima, Thomas? F of b. And why is that? So why are we calling f of b local? So when you say close to zero, well, it's not really. I I will tell you that f of b is a local maximum. B is kind of close to zero, but f of b is not. Does that matter? What do we think? It's a maximum on the domain from A to C. Okay. So if you're taking a smaller interval than the interval from A to E, or I guess it goes beyond A. But there's some smaller interval where B is or f of B is the highest value, right? Are we okay with that being a good reason for why that's the local max? That's basically it. I mean, we'll put some more formality behind it, but f of B is a local max, basically because there is an interval around B where f of B is the largest value. Are there any other local maximums? Or is it just that one? Oh, there's another one. F of B is, yeah. Why is f of B also a local max? Yeah. So I mean, f of D is the largest y value on that graph. And if I have some smaller subset, some smaller subinterval where D is the center of it, it's still going to be the biggest on that interval. Jordan? I mean, you got to be specific when you say extrema. And like I said, I haven't really defined it yet. I'm just kind of warming you up to it. But let's stick with this granted incomplete definition we're working from. Do we have any local minima? I got to vote for f of C and f of E and f of A. And here's the part where it's kind of confusing. F of E is a local minimum. F of C is a local minimum. Thomas, you have something? Okay. F of A is actually not. And the reason we're going to learn why is for it to be a local extreme point, either a minimum or a maximum, we have to have an interval centered on that point. So why don't I go to our next slide and we'll put some more specifics behind that. So if f of C is greater than f of x when x is near C, then f of C is a local maximum. So I know that word near is still pretty ambiguous. So let's talk about what that means. And I could replace this with or I could replace maximum with minimum, and definition would still hold. But if f of C is a local maximum, so let me draw a picture here. Some interval P, here's point C, and let's say that C is a local maximum. There's some positive number epsilon such that f of C is greater than f of x for every x on this little small interval. So everything within epsilon to the left and to the right. So, and really, I only have to be able to pick one value. And the distance on the right has to be equal. This is C plus epsilon. If I'm just looking inside this little window here, f of C is certainly the largest, right? So as long as I can do that, that's a local maximum. I'll pause there while you. Anybody have any questions? I want to go back a slide. Based on that definition, is it more clear why f of a is not a local minimum? Sebastian? Yeah, I mean, no matter what epsilon you pick, so no matter what positive number you give me, I can make it really, really small. My function is not even defined on that whole thing, right? So since a is the endpoint, there's nothing to the left that I can compare it to. How are we doing? Yeah, of course. So these are all about local extrema. Are we okay with the difference between local and absolute extremes? All right, let's go ahead and look at an example. So let's talk about where we should look for these things. So let's look at local extrema first. And it's quite a bit easier when you're looking at a graph. We won't always be looking at graphs. When we were looking for local extrema on this graph here, what kind of points do we look like? So what characteristics of the function, sorry, what properties does the function have at those points we have local extrema? So just to remind you, local extrema at when I say where should we look, I'm saying where might they be? So I hear the language, where do the function switches directions? So that's, and you're absolutely right. That's where it changes directions. So where is f prime of x equal to 0? So asking that question alone, would that have given us all the local extrema on this graph? Yeah, so I'll tell you this, the f prime of b, f prime of d, and f prime of e are all equal to 0. That's not true at f prime of c is not 0. What's happening at f prime of c? Thomas? Right, the derivative doesn't exist. So I'll say, where is f prime of x? Undefined. Or, and this is just an alternate language, where is f not differentiable? So clearly, if I have an interval around c, a small one, f of c will be the smallest value on that interval, but that derivative is not defined there. No, it is. It absolutely is. So remember, if we go back to our definition for local minima, local maxima, all that is required is that I have this epsilon window. So let me just take this little tiny window here. C minus epsilon, C plus epsilon. Is f of c the least value there? Yep. Yeah. So that's all that matters. So f of c is a local minimum. It's just you never would have found it if you're looking for then you would have found it. Sebastian. Oh, I'm showing I was showing tangent lines here. We're filling it out still. Anywhere else where we might be able to look for local extrema? That's what you need to look for local extrema is where's the derivative either equal to 0 or where is it not defined? How about global extrema? I'll tell you this, anywhere a local extremum so any point a local extremum might be a global one too. Where were the global max and min on this graph? So would we have found both of those only by looking at places where the derivative was equal to 0 or undefined? So what else do we need to look at? Well, let me ask it a different way. Why would we not have found that? Trying to think about the right way to ask this without just giving it away. So we needed to look at B, C, D, and E for local extrema because of the derivative, right? Well, we saw that A ended up being a global extremum, or f of A ended up being a global extremum. Right, that's the key here. Look at the endpoints of your interval. Because it seems like from the way this graph is behaving, if I were to have something, if this function was defined for x values less than a, it would be going even lower, right? So because of that, I can't look at the derivative. But since it's kind of achieved its minimum there, the function's not defined to the left of a, I have to look at my endpoints too. To clear why I have to look at the endpoints and not just the these other points that have to do with the derivative being undefined or being equal to 0. Or you ever raising your hand or okay? You were kind of in the middle. Any other questions? Okay. Let's look at an example here. I want to find the local and absolute extrema of this function here. And to be really explicit, I'm saying the domain is all real numbers. So because the domain is all real numbers, I can kind of ignore thinking about endpoints, right? So if I don't have to look at endpoints, what do I need to do to start looking for extrema? I can do better. It means yes, I can find where it's differentiable, but where it is differentiable, what do I want to look for a little further? Right. So since I am not looking at endpoints, really all I'm looking for these places where f prime of x is 0 or f prime of x does not exist. So if that's true, what do we need to do? Need a derivative, right? What's the derivative of cosine of x? Negative sine of x. So we want negative sine of x equals 0, where I could really just look at sine of x equals 0. So we're looking at a derivative of that function is equal to sine of x. Is there any value of x where that function is going to be undefined? Sine of x is continuous for all real numbers, so I can stop worrying about this. I'm really only looking at where sine of x is equal to 0. So if sine of x is equal to 0, what does that mean x is equal to? Nope, 0. Yeah, so I'll do it like this. Because there's really infinite number of places where this is true, right? Every integer multiple of pi. So k pi, where k is an integer, any multiple pi, any integer multiple pi. So those are all the x values where extrema are going to exist, right? So now we need to find something a little more specific. Let's find the minimum and the maximum. Our function is cosine x. Do we already know what the minimum values and maximum values are going to be? Yeah, so the minimum is going to be -1. And the maximum is going to be +1. But now we should think about where those are going to take place. So we know that the minimum values might occur at -pi, 0, pi, whatever, but it might not occur at all. So let's figure out, basically what we're going to do is figure out where cosine is equal to -1. So let's just ask a few of these. What's the cosine of -pi? Cosine of 0? Cosine of +pi? And so on. Okay. So can we generalize this to say where our maximum and minimum values are going to be? Every odd multiple of pi, right? So the minimums are going to be, I'll write it like this. 1 plus 2k pi, 1 plus 2k, all times pi, -1, where k is an integer. So that'll happen at pi, 3 pi, 5 pi, 7 pi, and so on, right? And then the maximum values are going to take place at every even multiple of pi. So in this case, how many local minima do I have? It's infinitely many, right? Same with maxima, right? So yeah, because I'm not restricting domain, I have an all right, let's look at a parabola. Again, I want the domain to be all reals. So no endpoints. So where do I need to look for extreme values? Or how do I need to look for them? What if you didn't know what this looked like? How would you start looking for them? Yeah, mean a derivative, right? So we're going to find out that you're right. So derivative is 2x. That's equal to 0. So our only x value we really have to look at is x equals 0, right? Let's pretend we don't know what this graph looks like mentally. How would we find out if that's a minimum or a maximum, or maybe it's neither one? Okay. So f of 0 equals 0. Does that tell you if it's a minimum or a maximum? There's something else we could do. Okay. So f of -1 would be 1. F of 1 is? But what if, like, let's pretend this function is something a little more complicated than x squared. What if it looks like this? So we know it has a point at 0, 0, right? We know it has a point at -1, 1. We know it has a point at 1, 1. And did I stay back to that slide? This function looks like this, where it's just not differentiable at these two weird places. I mean, wouldn't that be a maximum? Yeah, let's instead of following the function on that subinterval like that, let's follow the derivative. Because here's what we know about the derivative. One thing is really important, but there's another kind of subtle thing that's more powerful. We know that the derivative is equal to 0 at one point, right? But we also know the derivative is equal to 0 nowhere else. Otherwise, we would have found it, right? It's a pretty simple equation. Is there any possible way the derivative could be undefined? 2x is going to always be well-defined. I can double whatever number I can think of. So let's look at the derivative instead. And we want to look at a point greater than 0 and a point smaller than 0. So what are some good examples we can choose? 1 and -1 are easy. Another derivative at x equals 0 is 0. What's the derivative at x equals -1? And +1? So you have a function that's decreasing up to a certain point and increasing everywhere afterwards. What does that say about it? Yeah, it's decreasing, not changing for an instant, and then increasing. That's a minimum. So that's a local and absolute minimum at 0, 0. No, because so we know the derivative, the only place where the derivative can be equal to 0 is x equals 0, right? And we know the derivative cannot be undefined anywhere because 2x is a polynomial. So because of that, the only way the derivative could go from negative to positive, think about the intermediate value theorem, the only way the derivative could go from negative to positive is if it was equal to 0 somewhere. And I have already found the only place where it could possibly be equal to 0. So let me ask this one more follow-up question to kind of solidify this, hopefully. I found the derivative was negative at one x value that was less than 0. What does that mean about the derivative for any value, any x value less than 0? It's negative for every x value. And by the same logic, the derivative is positive for every x value that's positive. So I found a local or absolute maximum. They were the same at 0, 0. Are there any maximum values to think about? Nope. So the only way we could have a maximum is if the maximum was also 0, 0. Because I only have one point where the derivative is equal to 0. So how do I know that 0, 0 is not also a maximum? Yeah. Here's one of many examples. F of 1 equals 1. I already did something great. There are no maxima. One thing I do want to ask you is, what if the domain instead was from -2 to +6? If the domain was from -2 to +6, would there be local maxima? There would be absolute maxima. What about local? Still no locals, but where would the absolute maximum be? Yeah, whatever f of 6 is, right? Yeah. Sebastian. Because instead of looking at, let's talk about this graphically. I think we all know what this graph looks like. Pretend I hit the origin. That right there has no maximum, right? But basically what I did is this. I replaced that function with this new one where so now does it have a maximum? An absolute maximum. And f of -2 is neither minimum or maximum because we already found the absolute maximum 0, 0. And f of -2 is not going to be as great as f of 6. Daniel? Yeah. That only applies for locals. Yeah, because the reason why that only applies to local maxima is absolute extrema can happen at endpoints. And if it's at an endpoint, I can't define that epsilon interval because it will only exist on one side. Yeah. If I didn't say that, I'm sorry. I needed to. Anything else here? All right. How about x cubed? So again, domain is all real numbers. So where do I need to look for extrema? I want to know where this derivative is equal to 0. Again, just one point, right? So how do I figure out if that's a local min or a local max? Yeah, the number line thing is very helpful. I want to find the derivative. Let's just choose -1 and 1 again. What is f prime of -1? What's f prime of 1? All right, so you have a function that increases to a certain point and increases afterwards. It's not any kind of extrema. So this has no local or global extrema. And just to remind you what this graph looks like, again, pretend I actually hit the origin that time. So as you move from left to right, this function is strictly increasing. So because of that, it can't have any local extrema. And since it has no endpoints and it has no local extrema, I can't have any absolute extrema either. Any questions there?
3 to 0, 5 to 3.
So, very good question. Always increasing. A function is increasing if, as you move from left to right, the function is at least as large. Yeah. Good question, though. Anything else about? All right. This time I am giving you a closed bounded interval. So this time the local extrema and the absolute extrema might be different things. So let's start by finding the locals, local extrema. If I want to do that, what do I got to do? What is the derivative of this thing? Okay, I want that to equal 0. So what can I factor out here? 12x. So x squared minus 4x plus 3. And I keep factoring. So what values of x do I have that I want to look at? 0, 1. So I have 3 candidates. I don't want to say they're local extrema. They might not be. I have 3 candidates for where local extrema might be. How can I figure out if they actually are? Yep. So let's look at, and this one's going to get a little more involved. I know that x or f prime is equal to 0, and x is equal to 0, 1, or 3. So how many test points do I need to choose to figure out what's going on? I need 4, right? Shout them out. What number should I use? -1. Could I use -2? I really don't want to use -2. Why not? It's outside the interval that I care about. So this function doesn't even live outside of, or out left of -1. All right, -1's a good candidate. What else? Here's a good one. Where's a good one? And unfortunately, we're stuck with a fraction. So let's get some derivatives for this function at those 4 test values. And hopefully that'll tell us about our extremes. If memory serves, this first one is -96. This one's -24. And this is positive 144. F's. But here's a, do I care what the numbers are? Do I care? Negative. So hopefully that doesn't feel like a cheat, but that's really all I care about, right? Anything else? But what am I looking at in this number line here? I'm not looking for absolute extrema. I'm just looking for, I'm trying to figure out if I have local extrema by looking at what the derivative's doing. So now let's think about what's happening at x equals 0. Derivative went from negative to 0 to positive. So what do I have at x equals 0? That's a minimum. So I have a local min at 0 what? 0, 0. What's going on at 1? Local max at the point 1 what? Not 1, 0. I believe it's 1, 5. How'd you get 5? How'd you get 5? At what f of 1 is. And then finally, what's happening at f of 3? That's a minimum. And help. Did this a couple hours ago and I should have wrote it down. All right, so I have 3 local extrema. So now I can look at absolute extrema. Unfortunately, I've already done a lot of the work because when you look for absolute extrema, you have to know where all the local extrema might be. What else do I have to look at? Or Sebastian, question? That's a good question. How do we know that 1, 5 is the local max? Who can answer that? I'll know what the derivative is doing. Let's rush. What else do I have to do to find the absolute extrema? What's f of negative 1? But it might be bigger than 5 too. In fact, it's 37, right? What's f of 4? 32? All right. So where's the absolute minimum? The absolute minimum was at 3, negative 27. That's a local and the absolute. Where's the absolute max? And f of 4 ended up being neither, but we needed to look for it anyway. Rule it out. Any questions here? I will leave it up and I will let you go. Stick around if you have any questions. Otherwise, I'll see you on Wednesday. If you want your quizzes, stick around. Well, my definition for is you have to share this or yeah, so you're both. I think right now. Yeah, no problem. You can always. What? So what you might do is rewrite a lot of that over. So yeah, that's one of those terms. I'm trying to get people to not use this point 6. Yeah. So if you look at the key, I didn't do it this way. Yeah. And the problem is if you do it correctly, just functional and everybody uses one to forget. So you get that one to improve, yeah, it looks so different and yeah. So we all like to. So basically, let's do the fun. All one. So four inverse cosine of 3x squared. So really the domain. Does this all come down to whether the domain? So I know that I need this -1. Basically, whatever 3x is to be bounded between -1 and so let's think about the function of cosine of x. The range of cosine of x. So yeah, really, this is kind of step one to get there, and then from there, just a matter of. So from there, and here's one thing. This might not be obvious to you, and if it's not, this right here is equivalent. So basically, if I'm saying something is in between negative A and positive A, I'm saying it has to be within. So that's, I just get rid of this. So from here, it's just a matter of solving. So if the absolute value of x squared is less or equal to 1/3. Yeah, you can't simply square root both sides. So I think probably the most direct way to do it there is this. Instead of looking at inequality, let's look at if I want 3x squared to be equal to 1. To solve this, I'll get x squared is x is equal to plus or minus 1 over radical 3. So here's what you know. You know that plus and minus. So you know that these two values give you the balance. Now what you got to figure out is this. You found the boundaries, now you just have to figure out is the domain. Is this part of the domain? Is this part of the domain? Is this part? I already know that these two things. I know those two things are in the domain, but probably one of them. Okay, so then if I test 0, let's just try it. If x is 0, if x is 1, is this defined? What's the inverse cosine? So yeah, there is no angle whose cosine is 3. No angle whose cosine is 3. So because of that, I mean, you got to do a little more testing there, but it might be easier to follow. Yeah. And the only difference from the domain of the function to the domain of the derivative is it's the same interval except it's open. I can't include the endpoints on the derivative. How would you do that? So I mean that's if you look at the key items, I mean, when you're looking at the real numbers, let's say the absolute value, let's not use x, let's use a. If the absolute value of a is 5, what can a be equal to? Either one, right? So if I say the absolute value of a is less than or equal to 5, then really a just has to be within 5 units of 0, right? So if you're okay with that, then that allows me to write this as -5 is less than or equal to a, which is that's the shortcut of the.
And for the
Yeah, the demand derivative is almost the same, except it's of course.
so my handwriting. Function here, we need to find like basically. So I did like a word here, and like I get like no, I
Let's.
like
What was it tangent of the inverse sine of x? So what's the triangle he's using?
right triangle with an angle x. X.
I'm going to call this y just to not have the same symbol.
Yeah.
So now, basically, you're looking for the tangent of this angle, right?
Yeah. And then I just did so sine y equals x, I guess.
Yeah.
I saw that. Should be plus or minus 1 minus. Kind of my question was like, how do I figure out whether it's going to be positive or negative whenever I'm not differentiating, but just putting it in the exact form? Because like I came in that home like a lot whenever I was trying to find the answers. I'm not sure.
So in this case, unless there's more information on it, I don't think you can know. Okay. Because I think, based on the information we have, I would call the tangent of y equal to plus or minus x over radical 1 minus x squared.
Yeah, this is
And actually, now that I'm thinking about it, I think it just has to be positive. Because it's all about, basically comes back to what the domain of these functions are. So When you're looking at inverse sine and inverse tangent, both of them are restricted to quadrants 1 and 4, right? So because of that, basically here are your two options. If the sine of x, sorry, if the sine of y is positive, then this value is going to be positive, and so is this one. So the tangent is going to be positive divided by positive. I mean, that's how I'm, but like think about it, let's say this angle is in quadrant 4, then the sine in quadrant 4 is negative. And actually I take it back. I think the best you can do is.
Well, and then
Is there any more information there?
that's not.
Right. Well, the tangent is restricted to those two quadrants, but yeah. Right. Well, for tangent to have inverse restricted, whether or not we're actually thinking about the inverse tangent. What did you say?
No, that's why I was confused.
All right. Why wouldn't I see some weird they wouldn't address it? My best guess is then that
This is not the only problem.
that's weird that it wasn't addressed. Yeah, why would they do that? Well, why could you? So this angle y can be quadrant 1 or quadrant 2. Oh, you know what? I think I'm wrong. X itself can be negative. So because of that, I think I was assuming that x had to be some positive number, which would make this negative x. But really, x can be. If x itself can be positive or negative, there's no reason to get into the rest of this positive negative case. It's a variable.
Yeah, but what?
I don't know. No good reason, just that assumption. So the final answer is the thing that I was fixated on was the fact that the tangent of this angle might be negative. But not having plus and minus sign here, this thing itself can still be negative. Because okay, the denominator clearly has to be positive, right? But x itself might be negative, which is negative overall. So there's no reason to account for positive and negative if this thing on its own might be positive or negative. Yeah. The what? So basically what you have here is, so this term on the left